Hello, everyone. Thank you for joining CADSpace on our Innovation Day 2022 journey. My name is Gabriel Davila. I'm the National Sales Manager here at CADSpace. It's always my pleasure to say a few words to our clients in these types of events. We really can't thank you enough for your support over the last year. It's been tough, but to give you an idea, we've successfully completed around 3,000 cases, and we've run about 1,000 hours of online training, and we've welcomed plenty of new customers to the wonderful world of SolidWorks. I'm sure we can all relate. It's been tough, but we've made it all through together. Back to our event. You've made it to day 3, and really it's the best day. We're going to be focusing on 3D experience, about how we can manage our product lifecycle on the cloud, and how we can integrate it into SolidWorks. In addition, we get to see simulation on the cloud, leveraging the power of Simulia and cloud computing, and closing off with modeling in your browser with 3D Sculptor. Thanks again for joining us in this different Innovation Day. I miss seeing everyone in person. I always enjoy catching up with all of you, hearing your stories, and of course, with a beer in hand. Hope you're all looking after yourselves and hope we can get back to doing this in person next year. And for now, enjoy these new enhancements.
When we connect SolidWorks to the 3D Experience platform, cloud data management is just a few clicks away. I'm working on Nemo Submersible as a part of the team. We are on a tight deadline to finish up the hatch design. I'll quickly insert fasteners on the latch mount using SolidWorks Toolbox. After a quick inspection on the drawing, and everything is up to date, and it's time to save to the cloud. Let me log in to the 3D Experience platform using the task pane, these indicators, and let's log in. Let's wait. So these indicators show which components need to be saved and are updated. SolidWorks is configured to automatically catalog and release the shared items, so all users can access their shared libraries online. The save dialog shows exactly which items require an update. I can also assign any item to a bookmark, such as related drawing files. Bookmarks, as its name suggests, a convenient way to flag them for easy access later on the process. Only the new or changed items need to be uploaded to the cloud. This makes efficient use of network bandwidth, but still ensures everything is up to date with offline and cloud data. As the leader of our team, I'm able to save my own designs, easy to use lifecycle operations like which helps to avoid accidental override. I can change its maturity stage from in work to release. And let's switch to bookmarks tab. As the detailing works continue, the bookmark will keep everything organized for quick access. Right now it's just one drawing and part file. I will change them to released. Also, that we can upload files to bookmarks like this PDF instruction sheet and the related SolidWorks Composer file. Most document types can be previewed interactively within the SolidWorks task pane. We don't need to launch any external viewing apps, right there from task pane. Also, now I remembered I have few backlogs of finished design that also needs to be uploaded to the cloud. Now I can automate this with the batch save. I just select my local design folders and assign them to the appropriate cloud space, and SolidWorks will take care of the rest. As the Nemo sub-design evolves, the team must respond to changes order quickly. So let me start to a few changes. A quick keyword or name search to results. I will preview it using 3D Play. And then let's quickly sketch out a concept idea to modify the wheel. Let me arrange it. Alright, I just want to get rid of the circular wheel and make it like a dog. The famous one with the Tesla. Roadster. Yep, there we go. Let's remove those two parts and change it to the sides. And we can directly open it from the task pane to SolidWorks. Before making any changes, it's best to find a parent version file and where it is being used by using relational search. So it is being used in master hatch assembly, and which can be directly accessed from right here from task pane, and we can open it in SolidWorks for further modifications. Let's wait. Here it is. To make changes, first I need to create a revision of the assembly and the hand wheel. And you will be able to see the changes on the status indicator straight away, the plus indicator there. Now let's replace it with the new revisions, and then we will resolve it so the team members cannot modify it while I'm on it. But still they can work on the other components of assembly while I am working on these components. The redesigned hand wheel looks great, but I need to update the drawing. The shared bookmarks give a quick access to the related drawing files. The drawing is now in sync with the part model. Let's save it to revision B, then set the part and drawing to a frozen state so they can be reviewed from our project manager. This is how cloud data management enabled us as a Nemo design team to be productive right away. We were able to safely store our data, manage changes, and design concurrently, all without ever leaving our familiar SolidWorks design environment.
When you test your product virtually or in the real world, naturally you are exploring numerous design options, evaluating how long they will last, and finding out when and where ultimate failure may occur. And it's not an easy task when simulating numerous physics and loading scenarios. Collecting and making the sense of all the data can be daunting and time-consuming. This is especially the case when design and analysis tools are disconnected or limited, but there is a better way. The 3D Experience platform provides a collection of best-in-class simulation apps built in with the industry-leading technology, including Abacus or FE-Safe, and connects seamlessly with the SolidWorks. Adam Analyst is working on the Nemo submarine, as you can see into the figure, to help them satisfy their safety and certification requirement. When it comes to the battery compartment and still he has few remaining tasks to do. So let's consider the case over here. With the depth rating of 100 meters, it is critical that the battery compartment can withstand a pressure beyond that depth to ensure the safe operation. At the same time, weight and cost must be reduced whenever possible. Adam considered the thickness of steel tube and stiffener and defines the associated dimension parameter to be optimized. He saves the updated model to the platform and launches the Model Assembly Design app for the simulation process. First mesh is created. The automated FEM recognizes a thin component of the model and creates a mid-surface and associated shell boundaries, all in one command. So as you can see into the following video that I'm going to apply the mesh values such as the mesh sizes, the element order, and you can call it as a publication name over there. So I'll just say OK, and the mesh preview will generate the meshing. The next step is Adam creates a structural scenario that defines the load and the boundary condition to simulate the maximum design depth rating. For that, I'm just going to apply the pressure acting on the body as well as the displacement. So I'm going to restrain the body into the X, Y, and Z axis, and afterwards we'll apply a pressure on the surface of the body. I'm just selecting the bodies and done. So once we are done with the boundary conditions, it's time to run the simulation. And just quickly go through the simulation and run the simulation. So once I simulate, you can see at a first glance of the result, it is obvious that the structure is over-designed. Adam launches a parametric design study app. Let's select the parameters and the goal of interest, and let's computer do the rest of work for us. When the study is done, you can just say go to the results and say yes. As Adam can easily interpret and compare the performance of the various configurations from here, the best design is even highlighted for him. With one click, a new model and the study with the optimal parameter is created. So Adam can take a closer look, but he has an additional task to do. So before completing this study, Adam will quickly go through the differentiation and select the best study that he can use for the other results to generate, and call this one as a best. Let's generate that one. The next thing is, let's apply the pressure load on the battery compartment that happens multiple times throughout the life of the Nemo. Another loading condition that repeats is the impact of the skip landing during the storage. So to simulate this secondary loading condition, Adam creates an explicit dynamic study to accurately capture the rapidly changing stresses from the landing cycle. To do that, he'll just apply the initial velocity and apply the gravity acting on the particular body. So how exactly does this skid come in contact with the floor? Adam lets the solver figure that out with one simple and yet powerful general contact interaction. To greatly decrease the solve time, Adam will go through the simulation and choose the simulation on cloud. For leveraging the high performance computational power, Adam can even shut down his computer while the simulation runs. The stress values are within the expected range, but how many times can Nemo withstand both this and pressured load? To reveal the answer, Adam sets up a durability study. He defines a fatigue load that captures both the events. For the explicit dynamic result, he includes all the increment to account for the fluctuation in the response. Adam also includes both the stress and strain in the calculation to improve the accuracy and to solve both high and low cycle fatigue. Both the sequences occur in the loading history, but they are exclusive events. So turn off the inter events transition option. Lastly, he defined the base surface finish and solved the results. The results are not only available to Adam, but they may be also viewed by other collaborators from their internet browser, so everyone can get the latest information instantly from one place. Adam's last task is to identify when and where the ultimate failure may occur if the Nemo gets too deep. Leveraging the same study set up from the first scenario, he defined the risk of buckling state which goes further than the typical eigenvalue buckling analysis and is well suited for unstable and non-linear collapse of structural, and it doesn't require setting up a complex dynamic analysis. Processing the result is simple too. Adam plots the load factor and visualize which areas of compartment will fail first. By using the 3D Experience platform to explore numerous design options, evaluate durability, and understand the critical loading events, Adam and his team were able to make informed, timely decisions to help fulfill their safety and certification requirements.
Innovation is the essence of product design and could be companies' biggest competitive advantage, which can substantially enhanced by using subdivisional modeling, as it's spontaneous, requires minutes of training, and changes are visualized in real time. Also, available on any device with an internet connection and compatibility with your existing SolidWorks workflows. I will be demonstrating the concept design process Nemo submersible both as an industrial designer and the mechanical engineer. Let's jump in 3D Sculpture as I will begin the initial body concept. Every concept design has a unique starting point. In this case, progress has already been made on the underlying frame of Nemo, which were designed in SolidWorks, and they are readily available for the reference. The other concepts are prepared hand sketch, as you can see it on the screen. I will begin to transform my creativity for the Nemo body directly from height to a 3D shape. Subd modeling gets its name from the loops of edges and vertices that surround the shape. The more there are, the more control we have. Similar to a spline in SolidWorks, it's better to start with less than more. Robot is the main on-screen manipulator for user input. The shape is always edited with respect to its position, so I can move it to the left edge to keep that side stationary. Pushing and pulling the geometry is the main interaction in subd modeling. The robot can be used to translate, rotate, and scale the shape as I am translating it right now. Fortunately, in X-shape, there are plenty of shortcuts. For example, I can shift, select two faces, those and the entire loop of faces in between are selected. By default, all faces have a C2 level of curvature continuity, ideal for any industry product design. However, select edges can be creased at any time to enhance the style. In this case, by dragging the slider, I can adjust the smoothness factor applied to this crease. Also, after selecting the vertices, I can swipe the mouse across the screen to influence the top row of vertices. Switching to the let me manage that one. Switching to the other orthogonal views makes it easy to size, shape and position this first subd body right where it should be. That's on the side. Let me place it in correct place. And let me reposition it so that width is appropriately correct. And let's change few minor corrections. The robot can also be repositioned onto the edge. This way I can precisely control the direction of its translation. There it is. Precision can be applied to the length of its translation too. An on-screen ruler appeared to snap to an exact dimension. Now that one side is done, I'm ready to move on the hood after a few minor changes to add more material on top of the hood. After this simple minor changes, yep, there it goes. So I can simply select the face and then use the extrude command from context menu to add the top portion of the hood. After pulling some faces over the center plane, that plane can be used to apply symmetry. All modifications will be replicated from side to side, in this case XY plane. To ensure the hood of the Nemo is perfectly flat, I can align the entities to a line. Moving its endpoints will translate and scale the entities while snapping them to a perfectly horizontal orientation. So that's creased, and let's wait for a few seconds, just a few more. Yep. And this will ensure that the top face will be flat. And let's align that top face to a straight line, and I will snap it to horizontal line based on the side view of handy sketch. Now that the general shape has been roughed out, I can focus on few finishing touches before sending this out for review. Here I'm going to add 2 horizontal loops. Let me fix that first. Yep, so it's within the limit. And now I will add 2 horizontal loops to the midsection to make way for the hole that will travel through it. So that's 2. Let me fix that. Drag it to the front. Yep, and yep, so now let's add some sections, and I will add a hole by selecting 2 opposing faces and also scoop the bottom first. Yep, and now it's time to make a hole. Once we select 2 opposing faces, the context toolbar will show us the extrude icon, which can be used to create a hole. Let's select the extrude icon from context toolbar, and there we go, we have a hole, and magically a loop of hole is appeared on the model. So after a few minutes, I have enough detail to share my concept with the rest of my team. The sub-D modeling capabilities in Xshape provide the fastest way to conceptualize in 3D, and as we can see it on this demonstration, it's definitely faster than sketching on paper. Alright, let's add color on it. But what about SolidWorks? What happens when the reference frame assembly is modified? Let's check in SolidWorks desktop connected to the 3D Experience platform. Let's check all of the Nemo design team's data is on the cloud and accessible directly in the SolidWorks task pane. To ensure my changes are not overridden by another collaborator, I just reserve the files I plan to modify. Searching through entire database takes a second before I find the components I'm looking for. After adding the propulsion, let me search the propulsion first. Here we go. So the propulsions are added. You can see there those 4 propulsions, and next will be the hatch. Let me add a hatch assembly. Again, we will search. There we go. Now I'm ready to save the changes. So I will just go and save the changes. Just like that, my modifications are securely stored to the cloud, accessible to anyone around the globe with proper permissions. Curious about progress? I can perform another search for the body design. Even though it was designed in X-Shape, I can drag it right into my SolidWorks assembly to do a quick visual check on how my recent additions might influence the body shape design. By activating a preview in 3D Play, I can sketch some annotations to indicate the adjustments needed to account for the newly added components. Then I can post them directly to our private design team community for members to see. X-Shape geometry comes in. So let me post this first. So I will be going to post this in our private group, and it's ready to be shared with all of our members. X-Shape geometry comes in as a flawless, watertight solid, ready for extrude cells, ribs, and any other features necessary to prepare for this product for manufacturing. The best part is they enable hybrid workflows, allowing you to stay in sync while working concurrently with the team. Let's get back to X-Shape as we revise the frame assembly and refine the body to its highest level of precision. As anyone working in X-Shape will receive a notification for a post, which will take them to a community where members can review the proposed changes and let others know we are working on it. As you can see, I have posted it and Ab gave me a few suggestions, and I also informed him I'm on it. A quick refresh to visualize the changes, and let's wait. So there we have the thrusters and the hatch assembly. Yep, and it's up to date with latest design. We can see the changes with added thruster and hatch on the top. To keep the design tree organized, I will create an ordered geometrical set to house the reference sketches. Let's convert the outer diameter of the hatch opening, as I need to create an opening, and let's save it under reference sketches. Alright, give me a few seconds. Alright, let's convert entities. For the hatch opening, there we go. Now we need sketch mode, and boom, I have converted entities. Now I can move to my sub-D modeling. Instead of adding a loop of vertices surrounding the entire perimeter of the body, I can add localized group of entities just by selecting the profiles. There, that's from context toolbar, and let me increase those. I am using shift select to select multiple edges, and it's time to align them. Now I can select the new loop of edges on the hood and the corresponding edges on the hatch. The align to curve command perfectly aligns X-Shape geometry to SolidWorks assembly. Just like style splines in SolidWorks help to parametrically control splines, the case view in X-Shape reveals the underlying constraints driving the curved surface, making it apparent when edges are out of alignment. After selecting the vertices in sequence, I can easily align them to each other The side view reveals that the front faces of the hood might not be in alignment. Once selected, I can select coincident from the context toolbar, just like mates in SolidWorks. To correct the angle of the front faces, I can select the entities by rotating a model and reposition the robot to the pivot point. Then the face can be snapped to on-screen protector specific angle as required. There we go. After a few more adjustments to the hood, it's time to design for the thruster. I will prepare a set for each one and let's manage it under design tree. Vertical thruster just for the rod and hose for the horizontal thruster. Using the cylinder shape and automatically creasing each end will make it easy for me to locate the first pathway in relation to the vertical thruster. In similar fashion, let me first manage the size of it so that it becomes perfectly aligned to the thrusters we have. Let's check if we have, yep. Let's make it a bit smaller in diameter. After a few modifications, you can see the vertical thrusters is ready. In similar fashion, I will be adding the model for modeling the negative space required for the horizontal thruster. And let me add the horizontal thruster. There are now 3 separate solid bodies that can be combined to form the final shape, just as in SolidWorks. And combine feature has multiple options for Boolean operation. The subtractions will be perfect for this one. And let's use the subtract similar to SolidWorks. And we have a body shape as required. Let's inspect the body. I also noticed the intersection between the vertical and horizontal pathways is little bit too high. Just to remedy this, I will need to lower the vertical thrusters since we managed our design tree beforehand, which will allow us to position the vertical thrusters path in relation to the horizontal thrusters path. Let me drag it down. Let's have a final look. It appears the body shape is complete in X shape. That looks perfect. Taking one final look at the overall shape, it appears the job is complete. Now we can jump back to SolidWorks and the model can further modified based on parametric features. X shape provides an unlimited amount of design freedom and flexibility, but we can use it to design much more than a concept just we did with the Nemo submersible.